All right. So tomorrow we're going to be doing some data collection for our launcher lab, our Ring of Fire lab. Then next week, Friday, you will be actually launching in the completing the lab, I think is the best way of saying it. So the Ring of Fire lab is, we're going to set up, so I'm assuming that everybody that has a unit circle project over there doesn't want it anymore, and it's now up to our discretion, because we're going to launch from that shelf back there. You're going to have a certain angle that your group is going to calculate for, and so you're going to launch a steel ball, a ball bearing at a certain angle, and your goal is to go through a hoop. We're going to put a Bunsen burner ring that we borrowed from science. We're going to put that up. You're going to go through that hoop. Then you're going to land it into a bottle cap, and you'll have all of that calculations for next week. Okay. If you are going to be absent, you need to make this up before the next week, Friday. Meaning you need to, and this is not just you copy somebody else's stuff. You have to come in and get that data from us. Okay? All right? That's one of those things. Okay? Test launching is the following Friday. This is a 10-point summative lab. Okay? So this goes in as your grade. This is one of the summatives that we have for this unit, and so that will be a summative for that. Okay? So with that being said, as a warm-up today, set up the parametric equation to model the path of the ball. If we've got how far can Jordan Love throw the football, if he throws it at an angle of 58 degrees, an initial velocity of 36 feet per second, and an initial height of 6 feet. Set up those equations right now for me, please. What do we got for the X equation to go along with Jordan Love throwing the football? X equation. 36 cosine of 58 degrees times t. Okay, what do we got for the Y equation? Negative 16
squared.
Listen. T squared plus
36.
yes? Graphic form. Way too much on the 100. We can go smaller on the 100. Yes? Now the question is, how far can he throw it? Right? So we need to find this point down here. Okay? That's where the ball hits the ground, so that we need to find how far he can throw it. Okay? So what we need to do then is we need to, let me move this actually over here. Actually, no, I can keep that one there. Okay? What we need to do then is we need to go back into our graph here, and we need to just graph now in function mode the y function. So that was negative 16. Instead of t squared, I'm going to go with x squared this time, plus 36 sine of 58 degrees times t, but instead of t, I'm going to go with x plus 6. So when I graph that one, that now tells me a couple of different things. First, let me adjust my window here. Window zoom, window settings. X's, I can go from negative 2 to 5 by 1s. Y's, I can go from negative 5 to 30 by 5s. Okay? So we can analyze this graph now for a couple of different things. First thing that we can analyze this graph for is we can, oops, that breaks this one. We can analyze this graph for how high the ball went. So the ball went a maximum height of 20.564 feet, and that happened 0.95 seconds after he released the ball. Okay? We can also analyze this graph for how long the ball was in the air. The ball was in the air for 2.0877 seconds. That one is the important one for us in this case, because now what we need to do then is we need to find that distance. So we are going to plug in this number, the airtime number, into our x equation to find that horizontal distance. So this would be x is going to equal 36 cosine of 58 degrees times 2.0877. Okay. So that becomes then just a regular old calculator. 36 cosine of 58 degrees times 2.0877. So that ball went a grand total of 39.8272 feet. Questions, comments, concerns, clarifications? We did all that already. Maximum height of the ball, we said was, oops, let me scroll back down to it. We said the maximum height was 20.564 feet. Okay. So that got all of those. Did we get all of our extension questions? Yep, fantastic. All right. Spitball is launched at an angle of 42 degrees with an initial height of 2 feet and an initial velocity of 23 feet per second. Question number 1, will it hit a person 12 feet away? Question number 2, how long until the spitball hits the ground if no one is struck? Question number 3, after 0.8 seconds, what is the position of the spitball in relative to the person launching it? And I thought that there was a, oh, I guess there's not a, is there not a D? Nope, there isn't a D. Okay? All right? So answer those 3 questions for me now. How tall do we want our person to be that we're aiming for? 6 feet? So it looks like we can definitely shrink it in. 5, 10. Oh, yeah. Okay, so there's that one. Then we've got this one. This changes to 23. This changes to 42. This changes to 2. I know I wish I could do it on the parametrics too. But you can't just do it on the parametrics. Or why you can't just tap. Because they're not touch screens. Yeah, that's why. Okay. All right, so then oops, I forgot to put in the person. Yeah, get rid of that one. Put in the person. We are 12 feet away. We are T, and whoops, tap the brakes, and we are 6 feet tall. We gonna hit that person?
Yes.
If we're 6 feet tall, right? But if we're a shorty like me and we're only 5 foot and something, like we're only 5.5 feet, let's say. Still hit it, but if we're a child, let's say, because hopefully we're not chucking spitballs here at school. Like if we're 4.5 feet tall, what happens to that spitball? Goes over the top of us, right? Okay, so we're kind of in that range of if depending on how tall the person is, if it flies over them or not. Okay. So will it hit a person 12 feet away? Yep, for sure. We've got enough. How long until the spitball hits the ground if no one is struck? How long is the spitball in the air? Air time right here? I analyzed the graph. Maximum and 0. Just a normal function. Yep. But you use x instead of t. So x is time. If you use t here, then you got to put in like a slider or something. You get all goofy because you're using the wrong variable. Yep. Okay. All right. And then lastly, we got to figure out what the position is after 8 seconds. So that would be 23 cosine of 42 degrees times 0.8. So after 0.8 seconds, we are 13.67 feet away, and we are 4.072 feet above the ground. Okay? That's how we do that algebraically. How we can also do that is we can go to our graph here and we can select trace. We can select graph trace. Now, what this is saying is, this is saying at 0 seconds, we're at the position 0 feet away from the person, 2 feet off the ground. Okay? And then you can scroll out until you get to 0.8. So there are the same numbers there. 13.674 feet away from the launcher, 4.072 feet off the ground. Okay? So we can calculate it either with math by plugging in 0.8 for t in our equations, or we can trace it out to that point on our graph. Okay? The nice thing is once you're in the trace mode too, you should be able to just type in 0.2 and then hit enter, and it'll take you right to 0.2. Or if you need to type in 0.8 again, just type in 0.8 and it jumps you right to. But you got to be in the trace mode in order to do that. Mm-hmm. Questions, comments, concerns, clarifications? Yes, Moose.
So we're plugging in the time into the y equation.
Both equations, because it asks for the position. It asks for what position is the spitball relative to the person. So we need to know how far away it is and where it is vertically.
So we plug that 0.8 into both t-values.
Both the t-value here and the t-value here and here.
And then you get the distance at height.
Yep. The x will give you the distance, y will give you the height.
Okay. Would it be easier to do that and plug it in, or would it be easier to do the tracing?
That's a you call, not a me call. Both of them got the same answer. Okay? Good times. You now, once again, try Christian Yelich. Christian Yelich hits a baseball, which is 3 feet above the ground with an initial velocity of 150 feet per second at an initial angle of 18 degrees. Will the ball clear a wall that's 20 feet high, 400 feet away? What is the maximum height of the ball? And that's it. Just those two questions.
Ooh, I got
All right,
it.
so we got the ball. That's going to be x of t is going to be
Wait, it didn't change. No, you have to put that sign. That's what's missing. Why does that have to be? No, this is cosine. Why does that have to be? Well, cosine and then your y's. I've been doing it. Well, that.
That's what. Ooh, no, mine still does that.
You can ask it. All right, you can ask. Why is it 14? Okay, you want me to change it? What do you want me to change it to? T? And then what I gotta change my T values to? 0 to 20, right? Okay. Does mine still make 20 feet? Because 4 times 5 is 20. I could have gone 2T there, right? And went from 0 to 10. I could have gone 10T there and went 0 to 2. You know what I mean? Yeah. So it doesn't really matter. As long as the end result is 20 feet. Yeah. All right, so let's go back to this one. Tab, and here we go. And so this one we needed it to be at 400. Oops, that breaks. Let's clear this first. 400, and I went 4T, and I went to
How do I change this?
5. Okay.
Push enter. Push
Enter.
Go. That's break though.
Yeah. And this one became, actually let's just clear it out,
You know what I mean?
150 cosine of 18 degrees
I'm giving up.
times T, negative 16 T squared
Let's redo it.
plus 150, not inverse sine, tap the brakes, sine of 18 degrees, close, T plus 3.
Why does T look like that?
Okay? Obviously, we're going to have to change our window. We got to go all the way out to at least 400. I'm going to go out to 450 just because we can. Looks like we're going to have to go higher, too.
No, I only think they're wearing caps. Doesn't matter.
Oops.
Oh, and then it's
yeah.
Home run, not a home run.
Not a home run.
Not a home run. Warning track power. Okay? Yeah.
I can't even get
Okay, so we got that one. Next question that was asked was, what is the maximum height of the ball? So now we're going to go into this one, and we're going to go, come on, Tab. Come on, Tab. Oh, don't do this to me now. There we go. Tab, and we're going to go negative 16x squared, but we're going to go here now. This is going to be 150. This is going to be 18 degrees, and this is going to be 3. Oops, not 33, just 3. Change my window. Maximum height of the ball is 36.57 feet. Okay, so the answer to these questions was no and 36.571 feet. Okay? Again, 2 reminders. 1, tomorrow is data collection day for your launcher lab. Make sure you're in class. If you're not, you're going to have to make that up sometime before Friday of next week. 2, if you turned in a unit circle project first semester and want to take it home today with you right now. Also, there's some pie plates back there from Pie Day. Take those home too today, because otherwise they're at our discretion and we're feeling that the room is a little cluttered, just so you know.